so let's move on to the topic of the evening. What we're going to do today is going to be called power series. Okay. So previously, our infinite series consisted of taking sums of numbers, right? We had like the harmonic series. It was 1 plus 1 over n. It was 1 plus 1 over 2 plus 1 over 3. So we were taking sums of constants. How about if we introduce a variable x into our infinite series? Okay, so instead of summing up specific numbers, we let it be a variable, say x. So that's roughly what a power series is. Okay, all right, so definition. A series of the form, okay, series of the form, so sigma. So our series is now going to start at n equals 0, as opposed to previously starting at n equals 1, okay? So that's not really anything to worry about. Nothing quite changes. So n equals 0 to infinity. Cn times x to the n. And if I just write out the first few terms of this guy, this will be c0 plus c1x plus c2x squared, and so on forever, where x is variable. Okay, so it's just a good old variable, and the cn's, the c sub n's, are just real numbers. Okay, so series of the form blah blah blah, where x is a variable and cn is an r, are in the real numbers, is called, so now we're actually going to put a name to this, is called a power series centered at x equals 0. Okay, so that's what we're defining, so I'm going to underline it. Power series centered at x equals 0. Okay, so just to repeat myself, this notation here, Cn, little symbol that looks like an E almost with the real number sign, this just means that the C sub n's are real numbers. Okay, that's what that highlighted notation means. Good, so first definition. Second one is going to be very, very similar. Okay, so second definition. A series of the form sigma n equals 0 to infinity, Cn now being multiplied by x minus a to the nth power. Okay. So again, the c sub n are real numbers, and also this a that we have here is a real number. Okay. Is called a power series centered at x equals a. Okay. At x equals a. So that's what we're defining here. Okay, and this x equals a is referring to this x minus a that we have in the series.
So wait, could C sub n, could that be different for every n? Could that be like a function of its own?
Yes, exactly. So C sub n is going to be some function of n. It's going to be a sequence, really. Mm-hmm.
So the do now wouldn't that technically be a power series? Wouldn't like a bunch of the stuff you've, well, Actually, most of them were n equals started at n equals 1, but other than that, I mean, there were anything with x squared in it would.
Yeah, so the difference in the previous series was that everything was a constant already. What we have here is now this variable x.
Oh, I somehow just noticed that there were 2 variables in there instead of 1.
Yes.
Yeah, it took me way too long to recognize that.
Yeah. So our series have variables now. So when we input a particular x value, then it will become our familiar series from before. But we're just keeping it in as a variable for now. All right, so here are the definitions. I think it would be good to just look at a few examples. So just so we get a little familiar with what these things look like in practice. So examples of power series. All right, so let's just look at 3 quick examples. Examples of power series. Okay. So first one, it's going to be the sum from n equals 0 to infinity of x to the nth power. Okay. So all this looks like, if I just write out the first couple terms, this is just 1 plus x squared plus x cubed, and so on forever. All right.
I'm just going to take a gander and say that diverges.
So the
Wait. It could be 0. X could be 0. Never mind.
Yeah, so we're going to look later. We're going to want to look at x values for when this guy converges. And you'll be surprised it does converge for other values other than 0. Okay, so this is a power series. Just note that this is a power series centered at x equals 0, okay? So maybe you just want to jot that down. This guy is centered at x equals 0.
So if it starts at n equals 1, then it's technically not a power series.
It still is a power series. It still is. This is just conventionally what we do for power series. They start at n equals 0. Okay, next example. Okay, so here's a nice example, which we're going to look at next class. This is the x to the nth power over n factorial. Okay. So just to write out the first few terms of this guy, it's going to be 1 plus x squared over 2 factorial plus x cubed over 3 factorial, and so on.
Is that a Maclaurin series polynomial?
Yes, this is a Maclaurin series. Awesome. We're going to be doing that on Monday.
What did you say? I caught like the general outline of that word, but I didn't catch the word itself.
Maclaurin.
Could you spell that in the chat?
So we're gonna look at that later on Monday. So I don't want to jump the gun here, but yes, Tom.
Sorry.
No. Great insight. Yeah. So again, this is centered at x equals 0. Okay. And Maclaurin is spelled M-A-C-L-A-U-R-I-N. So this is an example of a Maclaurin series. We're going to define that on Monday. Okay. Good. So this is centered at x equals 0. And let's look at one last example that's not necessarily centered at x equals 0.
Hold on. Sorry that I keep, but isn't like the factorial of 0 either 0 or undefined? And if so, wouldn't that make the first term above undefined?
Yeah. We define 0 factorial to be 1.
Oh.
Yes, to make things nice. So that's pretty much by definition. We define 0 factorial to be 1. There are other intuitive ways to justify that, but we just define it to be 1. Okay, last example for this. How about this guy? How about x minus 2 to the nth power over 3 to the n? Okay. So does someone want to tell me what x value this is centered at? This is centered at x equals what?
2.
2. Exactly. This is centered at x equals 2. Very cool. All right, and yeah. So let me just write out the first few terms of this. It'll be 1 plus x minus 2 over 3 plus x minus 2 squared over 9. Yep, over 9, and so on. All right, so these are really pretty much the same thing as our series from before, except now our summons, so these guys, so the summons here, they're going to have now x values in them. So they're functions, essentially. All right.
I really want to like figure out how to graph these on a graphing calculator, but at the same time, I don't even know what would be the x-axis and which one would be the y-axis.
Well, these functions are sometimes going to have nice closed forms, so you'll be able to graph them. We're going to get to all of this. All right, so those are some examples, and really the heart of this lecture is convergence of a power series. Okay, so that's what we're gonna look at next. Convergence of a power series. Okay. So let me just state what we're interested in. Or what we're going to be doing really. We're interested in finding out for which x values a given power series converges. A given power series converges. Okay. So essentially, we want to find out which numbers can we plug in for x will make that infinite series converge in the normal sense that we defined in previous classes. Okay. All right. So just as a little motivating example, we can actually do one really quickly. Let's look at the sum from n equals 0 to infinity of x to the nth power. So this is actually a geometric series. This is a geometric series, okay? With ratio r equal to x and initial term a equaling 1. Now, can someone tell me what the condition on the ratio needs to be for this thing to converge?
Needs to be less than 1?
Yes, but more specifically, the absolute value of the ratio needs to be less than 1. So we already know the x values for when this guy converges. This will converge if the absolute value of x is less than 1. So that's pretty cool. This was straight from our theorem about geometric series. If the absolute value of the ratio is less than 1, the series converges. So
Does this, how do we know that this carries across from n equals 1 to n equals 0?
So this is the same exact thing. So if you look,
because n equals 1, n minus 1, it's n minus 1, and then now it's just n. But
you see it, right?
because n is just 1 lower, it's shifted 1
yes,
down.
Exactly. So yeah, so Josh was saying that the geometric series looks a little different because it starts at n equals 0. So we compensate for that by making the exponent n as opposed to n minus 1. All right. So I really don't think you should worry too much about that. It's a very simple thing, and it doesn't cause any trouble. So just for our purposes, this is also a geometric series. Okay. All right, good. So this will converge if the absolute value of x is less than 1, or equivalently, if x is in the interval -1 to 1. All right, so what this is telling us is if I plug in a number from this interval, say 1/2, plug it into this power series, it will converge. All right. It will converge as a sum of numbers. All right, very cool. So this leads us to a theorem. So there are 3 possibilities regarding convergence of a power series. Regarding convergence of a power series. Okay, so this will come in the form of a theorem, okay? So theorem.
You're doing another case 1, case 2, case 3?
There's going to be 3 statements here. Yeah, there's going to be a case 1, case 2, case 3. Yeah. All right, so here is the theorem. So let this guy, Cn x minus a to the nth power, be a power series. Okay. Then the series satisfies precisely precisely one of the following properties. Satisfies precisely one of the following properties. Okay. So here are the statements. 1. The series converges at x equals a and diverges for all x not equal to a. Okay, so this is just telling us that it could be the case that it converges for just at the center of the power series, in which all the terms are 0. Okay, because if I plug in x equals a into here, I get 0. All right, number 2. The series converges for all real numbers, x. Okay, so it could be the case that no matter what real number x I plug into this guy, it will converge. Okay, third and final possibility. There is a number r greater than 0 such that the series converges if the absolute value of x minus a is less than r and diverges if the absolute value of x minus a is greater than r. Okay, so here are the 3 possibilities, and we're going to see each of these 3 possibilities in our examples. Okay. Okay, and Josh, I see your camera's upside down, which is slightly distracting.
Maybe your cameras are all upside down.
Would
I mean, who's to say?
Would you mind putting it normal? It's just a little distracted because it's funny. All right. Okay, so we have that, and now, thank you. So now we have just a few definitions, and then we'll get to examples, okay? So in the case of statement 3 of the theorem, in the case of statement 3, so that's this guy right here, we just want to attach a piece of terminology to the number r, okay? So in the case of statement 3 of the previous theorem, we call the number r, the radius of convergence, okay? Radius of convergence. That's what we call that number r. All right. So that's in the case of statement 3. All right, and one more definition. I'm sorry, this is a lot of writing, and then we'll get to examples. Second definition. Okay. The set of x values for which a power series converges, set of x values for which a power series converges is called, so we're going to have a name for this set of x values. It's called the interval of convergence. Interval of convergence. Okay, and finally, if the series converges for all x values, we say the radius of convergence r is infinity. The radius of convergence, capital R, equals infinity. Okay, so a lot of writing. So the radius of convergence is capital R equals infinity. Okay, so so we're not really saying that R is equal to infinity, because really a number can't equal infinity. This is more of just a convention, okay? So this equal sign is not in the mathematical sense. It's just a language thing. Okay, so let me jump to an example. Okay, so finally, we're going to get to some examples. So first guy we'll consider will be sum from n equals 0 to infinity of n over 4 to the nth power multiplied by x plus 3 to the nth power. Okay? All right, so how in the world do we go about seeing which x values make this thing converge? Well, what we do is we use the ratio test, okay? We use the ratio test on this guy. We use a ratio test and then find out, which x values make that limit capital L less than 1. Okay, that's the strategy. Because we know if the limit L is less than 1, by the ratio test, it will converge. So we just want to figure out which x values will force L to be less than 1. That's the strategy. All right, so let's see how it works. So it's pretty much the same as the do now activity. So we just set up this capital L limit. Okay, lim as n goes to infinity. So now it is important to use the absolute values. Okay, if you recall the statement of the ratio test, we needed to have absolute values. So we need them now. All right, so we do the n plus 1th term. So it's going to be n plus 1 multiplied by x plus 3 to the n plus 1 over 4 to the n plus 1. Hope we're okay with that. That's just the n plus 1th term. And now divide by the nth term. But I'm just going to multiply by the reciprocal since we're dividing fractions. So now let me multiply by the reciprocal of the nth term. So 4 to the n over n, x plus 3 to the nth power. Okay? So this is just the ratio test. I'm doing the quotient of the n plus 1th term divided by the nth term. All right. Now let's just work this out. So this will be equal to lim as n goes to infinity. Well, this 4 to the n is going to cancel with the 4 to the n here. So we're just going to be left with a single 4 at the bottom. Okay, so I hope you're okay with that. And then also, this x plus 3 to the n plus 1 power will, all but one of them will cancel with x plus 3 to the nth power. So we are left with just n plus 1 times x plus 3 over 4n. Okay? So any questions about this cancellation, these cancellations I've done? I'm just doing algebra at this point. Good. So after you do all of the power cancellations, it's a good idea to bring any terms involving x outside of the limit. Okay? Because this limit has to do with n, and x has nothing to do with n. So let me just rewrite this as I bring out the x plus 3 as so. Okay? Lim.
So the x plus 3 is the n plus 1 is multiple. Okay, yeah.
Yes, sorry. So the x plus 3 can be factored outside of the limit since it does not depend on n. Okay, so that was.
Oh yeah, it was just like I looked up and I was like, where are the doesn't have parentheses, and then I figured just that was probably because then I looked farther up and yeah.
Yeah, that was my bad. So yes, there should be parentheses around it, comes out as an absolute value, and now what's remaining inside of the absolute values is actually always positive. N plus 1 over 4n, this guy right here, that's always positive. So I need not put the absolute values, okay? So I hope that's okay with everyone. Absolute values can just go away now, since n plus 1 over 4n is always positive. Great. So this limit here, this just comes out to 1 over 4. You could use L'Hopital's, or you could just take the ratio of the leading coefficients. So this is 1/4 multiplied by x plus 3. Excellent. So here's where the ratio test comes into play. By the ratio test, this series will converge if this capital L, which we just figured out to be 1/4 times x plus 3, if this quantity is less than 1. Okay, so we set 1/4 times x plus 3 to be less than 1 and solve. That's what we do. So we set this guy 1/4 times x plus 3 to be less than 1 and then solve. All right, so I hope that's okay. So what we're doing is 1/4 multiplied by the absolute value x plus 3 less than 1, and I'm setting this. Okay, I'm setting it to be less than 1. And we solve. So is everyone okay with
Do people put like the colon in front of the greater than sign too, or does that just look too much like a frowny face for mathematicians?
Well, the colon is for when you're making like a definition. So we're not making a definition here. I'm just setting it to be less than 1. Okay, so I'm setting this to be less than 1 because I know it will converge if it is less than 1. So I want to see which x values will make this guy be less than 1. All right, so we solve this guy. So let me just multiply both sides by 4. This is x plus 3 is less than 4. And now this is why I considered this example in the beginning of class, how to solve these guys. So first of all, the radius of convergence is 4. So r equals 4, all right? And we see that by this number here. All right, now to find the interval of convergence, we solve. Okay, so this is just now -4 is less than x plus 3 is less than +4. This is just how you solve absolute value inequalities. And this is now -7 is less than x is less than 1. There we go. So we're done. Thus, the interval -7, 1 is the interval of convergence. Is the interval of convergence. There we go. So really the final answer for these types of questions is you need to tell me the radius of convergence, which we found to be 4, and then you need to tell me the interval of convergence. Right. So I hope this strategy is clear. We're just using the ratio test and seeing which x values force capital L to be less than 1. Right. All right, so let's do a slightly more complicated example. Okay. So if you need me to scroll up, please just let me know. All right, so let's look at sum from n equals 1 to infinity. You'll see why we're starting at n equals 1. This is going to be 2 to the 3n over n multiplied by x minus 2 to the nth power. Okay. So 2 to the 3n power. All right, and we're starting the sum at n equals 1 because if we started it at n equals 0, it would cause division by 0, which is not allowed. Okay. So that's why we started at n equals 1. All right, so it's the same thing as before. We just have to set up this limit L. So let's do it. So L will be this limit as n goes to infinity. So we need absolute values now, okay? Very good. So what's the n plus 1th term going to look like? So it's going to be 2 to the 3n plus 3 over n plus 1 multiplied by x minus 2 to the n plus 1. That's the n plus 1th term. Is everyone okay with the exponent being 3n plus 3? Now, I'm going to multiply by the reciprocal of the nth term since we're dividing fractions. All right, so let me multiply by the reciprocal of the nth term. So this will just be n over 2 to the 3n times x minus 2 to the n. There we go. Very good. So we're going to get a lot of nice cancellations here. So this will be lim as n goes to infinity. Well, let's take care of these powers of 2. This is going to be 2 to the 3n times 2 cubed. So the 2 to the 3n will cancel out. We're just going to be left with 2 cubed, right? Let me 2 cubed up top. X minus 2 to the n plus 1 will combine with this guy just to leave x minus 2 to the first power. Okay. So if that's okay. And then it's over n plus 1 times n. Okay, so just please let me know if these simplifications are clear. So I'm just skipping a few steps here. All right, good. So this factor here, 2 cubed times x minus 2, that can be taken outside of the limit, okay? So that's going to be 8 multiplied by the absolute value of x minus 2 times a limit. And now what's left in the limit is positive. So I will not write the absolute values. N over n plus 1. Okay. Good. And what is this limit equal to? Well, that's just,
1.
yes, 1, exactly. Good, good. So I'm just going to write this as 8 multiplied by the absolute value of x minus 2. Very good. So now we need to set this to be less than 1. Now, we set, so that's the important word, we set this to be less than 1. We set this, meaning that guy, we set this to be less than 1 and solve. That is the procedure. All right, so let's do it. So let's do 8 multiplied by absolute value of x minus 2 less than 1. And I'm just going to put a little set above this less than sign just to make it clear that we're setting it to be less than 1. Good. So let me divide both sides by 8. This is x minus 2 is less than 1/8. 1 over 8. All right, so here we see immediately that the radius of convergence is 1/8. Okay, so that's the first thing. And now let's solve. So this is now x minus 2. That's sandwiched between -1/8 and 1/8. Yeah, -1/8 and 1/8. Very good. And then if you just work out this arithmetic, you will get that this is 15 over 8 is less than x, which is less than 17 over 8. Okay. So that's
Wait, you just. Oh wait, yeah. Sorry, I was.
So I just added 2 to all 3 sides of the inequality. And then I did the fraction arithmetic. All right, and there we go. And just typically, we like to write this set of numbers in interval notation, okay? So thus, the interval of convergence is just going to be the interval 15 over 8, comma, 17 over 8. That's all. All right, so you're not wrong if you stop here, but it's nice to just write it in the interval notation. All right.
Okay, I have a question when it comes to, because I know when we did the test, we had to say, and this converges because of the limit convergence test or what have you. When we do this, do we also have to put thus the interval of convergence is in our answers? Like put those words in?
Oh,
Or is that more or less to just show us what we're doing, like in the class right now?
I'm trying to be instructive here to just tell you what this is.
Got it.
Yeah, no, you can just write 15 over 8, 17 over 8, yeah, but it never hurts to be super clear, but that's that. Trying to organize, hold on. All right, so here is a really nice example. So let's just continue with this. So we're going to look at the infinite sum, or the power series now. From n equals 0 to infinity, it's going to be x to the nth power over n factorial. So we're seeing this example come up again. All right, and again, we are interested in looking for the radius of convergence and the interval of convergence. That is the x values that I can plug into this guy that will make this series converge, all right? So the strategy is the same. We look at this limit capital L. Okay. Good, but we need absolute values now. So it's going to be the n plus 1th term, so x to the n plus 1 over n plus 1 factorial. And now let me multiply by the reciprocal of the nth term, since we're dividing fractions. It's the n factorial over x to the n. Okay, so now let me just apply that property of factorials to the n plus 1 factorial on the bottom. So this will be x to the n plus 1, x to the n plus 1th power. Now, n plus 1 factorial can be equivalently written as n factorial times n plus 1. All right, so that was that nice recursive property of factorials. All right, and now everything else is the same. And the point of doing so is that we get a lot of nice cancellations. So the n factorial and the n factorial cancel, and x to the n plus 1 over x to the n, that just comes out to be x. So this is lim as n goes to infinity. This is just, yeah, x over n plus 1. Mm-hmm. Yes. All right. So just let me know if any of these simplifications are confusing. Good. So next, after we do all of the canceling of the powers, we want to bring out our x expression outside of the limit. That's usually the next step. So it's going to be absolute value of x multiplied by the lim as n goes to infinity. 1 over n plus 1 is always positive, so I'm not going to write it with an absolute value. Okay, we're good. This is kind of interesting. This limit comes out to 0. 0. So what was next in our set of steps? We set this to be less than 1 and solve. Okay. Well, the funny thing here is that this inequality holds for any x value I plug into it. Okay, so this inequality holds for all x values. Holds for all x values. So this limit, capital L, will be less than 1 no matter what x value I plug into the power series. So the radius of convergence is infinity. Thus, R is infinity, and the interval of convergence, is just going to be the interval minus infinity to positive infinity. Okay? So this holds true no matter what x value I plug in. So the radius of convergence is infinity. So that's a really nice example, and we're going to see this series pop up on Monday. Okay, so we saw one where every x value worked. How about one where no x value works? So let's look at that. Let's look at the sum from n equals 0 to infinity. This is going to be n factorial times x to the n. All right, so just like before, let's set up that limit capital L. So lim as n goes to infinity. So the n plus 1th term will just be n plus 1 factorial times x to the n plus 1. Yes? And since we're actually not dealing with fractions for the first time in a while, I can just divide by the nth term, which is what we were doing all the other times. So this is now n factorial times x to the n. All right, so this is just good old ratio test, n plus 1th term divided by the nth term. Okay, so let's use our property of factorials. So this is the lim as n goes to infinity. So I hope you guys agree that this factorial, n plus 1 factorial over n factorial, will just simplify to n plus 1. Okay. So that's this right here. This comes down to just n plus 1. And x to the n plus 1 divided by x to the n, that just becomes x. Okay. Okay, is everyone okay with that simplification? Good, so now let me pull out that absolute value of x. So this would be absolute value of x times lim as n goes to infinity of n plus 1. Okay, and what does this limit evaluate to? Well, this limit is infinity. Okay. So the next step was to now set this to be less than 1, set. Okay, and this looks quite silly. We see that no x values will solve this inequality, okay, because infinity it will never be less than 1, okay? So no x values solve this inequality. Okay. Thus, the radius of convergence is 0, and the series only converges if x is equal to 0. So that was, I think, possibility 1 of our theorem. All right, so I hope everyone is okay with why it's no x values work here, okay? Because infinity will never be less than 1. So any questions? Okay. All right, so let's move on to the next thing. So the next heading that we'll work under, this is going to be called representing functions as power series, okay? Representing functions as power series. Okay, so let's go back to the series x to the nth power, okay? So let's consider the geometric series. The geometric series, the sum from n equals 0 to infinity of x to the nth power. Okay, so we looked at this at the beginning of class. So it has initial term, it has initial term, a equaling 1, okay, I hope that's clear, and ratio r equaling x, okay? And this will converge. This will converge if the absolute value of x is less than 1. Thus, so do you guys remember our nice formula for what a geometric series converges to if the ratio is less than 1? So thus, we actually have a nice closed expression for this guy. So the sum from n equals 0 to infinity of x to the n equals a over 1 minus r. Okay, so that should look familiar. And now we just plug in our a and our r. Our a is 1, and our r is x. This is 1 over 1 minus x. Okay, so we're just applying that formula for when a geometric series converges. Now, I need to point out that these equal signs are only valid if the absolute value of x is less than 1. Very important. This is only true in that interval -1 to 1, okay? So I hope everyone is okay with how I obtained these equal signs. So this is an extremely useful fact, this highlighted portion here, all right? So let me just write this down. This is a very useful fact and allows us to represent other functions as a power series, represent other functions as a power series. Okay, so we're going to be calling upon this highlighted portion, this identity, over and over again. Okay, very useful. So please tell me now if you want me to explain this again, because it's very fundamental. Okay. All right, so if I may, I will move on to the first example. Okay. So the prompt is to write 1 over 1 minus x squared as a power series. Okay. So that's going to be something that you'll be asked to do on the homework. So this is like a nice practice question. All right, good. So how do we deal with this? Well, we just need to look at the geometric series formula for convergence. So note that 1 over 1 minus x squared is the sum. It's the sum of the geometric series whose initial term a equals 1 and ratio r is what? X squared. So this is a over 1 minus r. But a is 1 in this definitive case, and our ratio is x squared. All right, so that's how we're getting this. A is 1, and our ratio is x squared. There we go. Right, so just recall, this is only the sum of the geometric series whenever, we need to write this, whenever the absolute value of x squared is less than 1. Okay, so what I've written here only works if that ratio is less than 1. Okay, so thus, let's just put it all together. 1 over 1 minus x squared, this will equal infinite sum from n equals 0 to infinity, it's just going to be that ratio to the nth power. Okay. So this is our R. All right, so I know this is slightly different than previously because the power is n and not n minus 1, but do not worry about that, okay? And then we can simplify this a little more. We can use properties of exponents to multiply the two powers. So it actually takes the final form, n equals 0 to infinity of x to the 2n, okay? So we have just represented our function 1 over 1 minus x squared as an infinite series. All right. So this identity is only valid for absolute value of x squared being less than 1, which is really the same as saying the absolute value of x is less than 1. Okay, so you really need to put this here. You need to tell me for which x values this identity is valid. Okay, we need that ratio to be less than 1. All right, so any questions on what I've done here? All right, so let's move on then. Okay, so how about let's write 1 over 1 plus x as a power series. As a power series, okay? All right, so we need to be a little clever. We just need to rewrite this guy as 1 over 1 minus something, okay? So let's just do that. Note that 1 over 1 plus x, I hope you'll agree with me, this is the same as 1 over 1 minus negative x. Okay. And the reason why I did that is because our geometric series formula needs to have a minus sign in it. It's a over 1 minus the ratio. Okay. Good. Now we see that this highlighted portion is the sum of the geometric series with initial term a equaling 1 and ratio r. Well, in this case, it's negative x. Okay, I hope that is clear. It's whatever you're subtracting. Okay, so we're subtracting negative x. Good. Which converges if the absolute value of x, of negative x, sorry, is less than 1. Well, this is just the same as absolute value of x being less than 1. All right, I hope that's clear. All right, so we're pretty much done now. Thus, 1 over 1 plus x, this will equal sum from n equals 0 to infinity. So it's going to be the ratio to the nth power. Okay. And why is that negative x in parentheses? Because that's our r value. Okay. Good. So this is technically a final answer, but you can clean it up a little bit. So typically we'll see this rewritten as, you can pull out the negative 1 to the nth power. Okay, so this is negative 1 to the nth power multiplied by x to the nth power. Okay. All right, and we just need to make note, this is valid. These equal signs are valid for when our ratio is less than 1. Okay, so that highlighted portion for when absolute value of x is less than 1. Okay, so we need to make that statement. So what we've done here is we've taken this rational function 1 over 1 plus x, and we've rewritten it as an infinite series. Okay, so that's kind of interesting. Good. Okay, so I'll do another example if that's okay. So let's look at, let's write 1 over 4 minus x squared as a power series. Okay. So what we need to do here is we need to algebraically rewrite 1 over 4 minus x squared as 1 over 1 minus something, because that's what that's the formula for the sum of a geometric series. So that's what we'll do. That's the first step. So we rewrite as so. Rewrite as, okay, so 1 over 4 minus x squared, that's the same thing as 1 over 4 multiplied by 1 minus x squared over 4. Okay, so I factored a 4 out from the denominator. Okay, and that was just to introduce a 1 there. We need a 1, okay? And now you can just rewrite this as 2 separate fractions. This is 1/4 multiplied by 1 over 1 minus x squared over 4.
So 1/4 is a?
Yes, pretty much, yes. So you can think of it how Josh said, as a being 1/4, or you can just deal with this second factor separately and then multiply it by 1/4 at the end, okay? So let's just do it that way. So the second factor, which I've highlighted, 1 over 1 minus x squared over 4. Okay, this is now in a nice form for us. It's 1 over 1 minus something. Okay, the second factor is the sum of the geometric series with initial term a being 1 and ratio r being x squared over 4. Okay, so we're essentially we're using the geometric sum formula in reverse. Okay. So that's it. We have identified our initial term and our ratio. So now we can do this. Now we can rewrite this as an infinite series. Thus, 1 over 4 minus x squared. Okay. So I'm just going to bring down this 1/4 from the beginning. So that's just 1/4. And now the second factor I write as an infinite series. 1/4 times the infinite sum from n equals 0 to infinity. It's just the ratio to the nth power. So it's going to be x squared over 4 to the nth power. All right. And this is the reason why that is in the parentheses is because that's our ratio. Okay. So now you can just clean this up a little. Bit. You can bring the 1/4 into the sum. So this will just be the sum from n equals 0 to infinity, x to the 2n over 4 to the n plus 1 power. All right. So just let me know if you're not okay with this algebra step I did. Brought the 1/4 in, and then I used properties of exponents. Good. So we're not done yet. We need to say for which x values this is valid for, okay? This is valid for when the ratio, the absolute value of the ratio, x squared over 4 is less than 1, okay? So this needs to be said. Remember, geometric series only converge if the absolute value of the ratio is less than 1. All right, good. So now we just can solve this very simply. This is the same as the absolute value of x squared being less than 4. Multiply both sides by 4. And this is the same as absolute value of x being less than 2. All right. So this is valid for when the absolute value of x is less than 2. Just trying to figure out which example to do. Okay. All right. So we'll just do one more example like this, and then I think we'll take a break, okay? So, example. I'll always do that. Okay. And as always, please stop me if you have any questions, all right? All right, so this one is more or less the same as the others. We're gonna write 3x over 1 plus x squared as a power series. Okay, and remember the goal, we want to algebraically manipulate this so it's of the form 1 over 1 minus something. Okay, so that's what we'll set out to do. So 3x over 1 plus x squared, this is equal to 3x multiplied by 1 over 1 minus negative x squared. Okay? All right, so I hope that's okay. And now I'm just going to jump straight to the series. This is now 3x, and this second factor here, I rewrite as an infinite sum. Okay, this is a geometric series with ratio negative x squared. Negative x squared to the nth power. All right, so here's the ratio r. That's why I put it right there. Okay, so technically this is completed, but we just like to, usually we just like to clean this up a bit. So if you just play around with this a little bit, you'll get that this is the same as 3 times negative 1 to the nth power times x to the 2n plus 1 power. All right. And that's just by algebra and properties of exponents. All right, so just check that. Okay. Good, so we're not done yet. We just need to state which x values this is valid for, okay? So this is valid when the absolute value of the ratio, so negative x squared. This is valid when the absolute value of negative x squared is less than 1. This is the same as the absolute value of x squared less than 1, which is the same as the absolute value of x is less than 1. Okay, so it's valid precisely when the absolute value of x is less than 1. All right. Very cool. All right, just see. Skipping that. Okay, one small thing, and then we will do a break, okay? So let's actually go in reverse. So what we were just doing is I was giving you a function, and then you were writing it as a power series. How about if I give you a power series, tell me the function that it represents? All right, so let's just do the reverse of this, okay? So, example. So which function is represented? So I'm going to give you a power series. You tell me which function it is. Which function is represented by the power series? Okay, so sum from n equals 0 to infinity, 2 to the n multiplied by x to the n. Okay. All right. So all you need to do here is just rewrite it as a geometric series. Okay. So this is the same as absolute value of the infinite sum from n equals 0 to infinity. So let me just combine these two factors as 2x to the nth power. Right. It's the same thing. It's by properties of exponents. And now it's immediately recognizable as a geometric series, okay? Which is geometric with initial term 1 and ratio r equaling 2x, okay? Okay, this converges. So remember, this will converge if the absolute value of r is less than 1. So this converges if absolute value of 2x is less than 1, which is the same as the absolute value of x being less than 1/2. Very good. So if the absolute value of x is less than 1/2, this is equal to a over 1 minus r. That's our geometric series formula. And now let's just plug in all of our info. A is 1. And what's our ratio? 2x. So it's going to be 1 over 1 minus 2x. All right. So that's what we did. So what we have done here is I gave you a power series, and then we figured out the function that it represents. All right. And we just need to note that these things are only equal to each other if the absolute value of x is less than 1/2. Okay, so that needs to be stated. All right, very cool. So we'll do a break now. So let's do a break for like 10 minutes, and then we will finish up for the night. Okay, let's do 7:45. Okay. So the final topic of tonight's class. So we want to actually do some calculus with these power series. Okay, so we want to take derivatives and integrals of these power series. So how do we go about doing such a thing? Okay, so last topic of the night, the heading is going to be differentiation, and integration. Integration of power series. Okay, so we just want to do some calculus with these things. Okay. All right, and it's not as hard as one would think. All right, so this is actually going to come in the form of a theorem. So it's going to be a theorem, and then we'll apply the theorem. Okay, so here's how it works. So suppose, so we're going to define f of x to be a power series. Okay, I'm just going to give it a name. So f of x, suppose that's a power series, n equals 0 to infinity, c sub n multiplied by x minus a to the nth power. So that was our power series. So suppose this guy has radius of convergence, capital R. Okay, So this thing will converge for some x values in a radius of convergence capital R. Okay, so what can we say about f prime of x and the integral of f? That's what this theorem is going to tell us. Then f prime of x, the derivative of f, is equal to n equals 0 to infinity. So it's actually, you just use the power rule on each summand, okay? So it's n multiplied by cn multiplied by x minus a to the n minus 1 power, okay? So this is not at all obvious. You just can't differentiate an infinite series term by term to get the derivative. But it actually ends up being, after proving it, it is true, okay? So the derivative is as such, and the integral, and we also have a nice expression for the integral of f, or the antiderivative of f. This is going to be some constant, c, okay? So you know how we get a plus c when we take integrals? C plus the infinite series. It's going to be cn multiplied by x minus a to the n plus 1 power divided by n plus 1. Okay? So it looks like we have applied the power rule of integration to each term of the series. Okay? So I hope you can kind of see what happened here. All right? These are not obvious at all. You do need to prove this, but we're not going to. We're not going to prove this. All right, so we have expressions for the integral of f and the derivative, and we need to say something about its radius of convergence. And both of these series also have radius of convergence capital R. So that's cool. Radius of convergence capital R. Okay, so they share the same radius of convergence that the initial series does, okay? All right, so let me just quickly say in English what this theorem is telling us. So note, this theorem tells us, that to differentiate / integrate a power series, so this is just an intuitive explanation. This theorem tells us that to differentiate or integrate a power series, we can differentiate or integrate term by term. As long as we're within the radius of convergence, or the interval of convergence. So we can differentiate, integrate term by term, as long as we're within the interval of convergence, okay? Interval of convergence. Okay, so let's just take a second to get that down. Okay, so when I say differentiate, integrate term by term, well, look, I'm literally just differentiating each term of the power series. I'm using the power rule on it, and I'm getting this, right? Isn't this just the power rule? I'm bringing the exponent down as a coefficient, and I'm subtracting 1. So I'm differentiating the power series term by term. Okay, and similarly, I'm integrating term by term. I'm hitting each term with the power rule of integration, which is to add 1 to the power and divide by the new power. Okay, so that's really what this theorem is telling us. And surprisingly, it's hard to prove. So that's that. So here we go. We're just going to look at a few applications of this theorem, and then we're going to be done. So applications of previous theorem. Applications. Applications of previous theorem. All right, so we're going to use this theorem to actually come up with new power series expansions, okay? So, our task is going to be to find the power series, for the function 1 over the quantity 1 minus x squared, okay? So we're going to use this theorem to get the power series for this guy, this 1 over 1 minus x quantity squared, okay? And you'll see how. So the key piece to notice is that 1 over 1 minus x squared, this is actually the derivative of an expression we have used before today. So note that 1 over 1 minus x squared is actually the derivative, d over dx, that's how we denote the derivative of a function, 1 over 1 minus x, okay? So I hope you agree with me. If I take the derivative of 1 over 1 minus x, I will obtain the left-hand side of this equality, okay? So what we want to do is actually differentiate the power series for this guy, okay? And that's what the theorem tells us we can do, all right? So thus, we can differentiate. We can differentiate 1 over 1 minus x, which we have figured out to be, so if you'll recall from earlier, this is nothing other than x, the infinite series of x to the nth power. So we can differentiate this guy term by term, okay? And that's a very easy thing to do. Thus, we can differentiate this infinite series term by term, okay, to obtain the power series for 1 over 1 minus x squared, which is what we want. Okay, so I hope the strategy of the theorem is clear, okay, and how we're using the theorem. Okay. Very good. So this is now a very simple matter. So here we go. So we have that 1 over 1 minus x squared, okay? This is d by dx of the infinite series now of x to the n, okay? Very good. And here is where we use the theorem. The theorem tells us we can actually slip this differential operator, this d by dx, inside the series, okay? So this is the same as, excuse me, sorry. This is now the same as the infinite sum of d by dx of x to the nth power, okay? This is by the theorem. The fact that I can move that d by dx into the infinite series, okay? That is where we're using the theorem, okay? There we go. And now this is very simple. We can just apply the power rule of differentiation to x to the n. And that's just n multiplied by x to the n minus 1 power. That's it. All right, so that's it. We have a power series for 1 over 1 minus x quantity squared, but as usual, we need to say when this thing converges, okay? So, which converges? It's going to have the same radius of convergence as the thing that we started with, okay? And that was 1. Okay. All right. So let me just repeat myself. This converges when absolute value of x is less than 1 because the thing that we're taking the derivative of converges when absolute value of x is less than 1. Okay, that's what the theorem told us, that the original thing and the derivative both had the same radius of convergence. So this is also by the theorem. Okay, this fact right here, that's also by the theorem. Alrighty. So just let me know if you have any questions. All right, so let's move on with some further examples. So let's find the power series. Let's find the power series for 2 over the quantity 1 minus x cubed. The whole quantity cubed. So what we would like to do is to realize this function, 2 over 1 minus x cubed, as the derivative of something. Okay, so let's do that right now. We have that our original function that we're given, 2 over 1 minus x cubed, this is actually the derivative of, okay, of the thing we just did previously, of the example we just did previously, 1 over 1 minus x squared. Okay? So if you just take the derivative of this guy, just convince yourself, you will in fact get the left-hand side of the equality, all right? So that's very nice. And we already have a power series expression for this thing by the previous example, okay? Thus, by the previous example. We'll have that 2 over 1 minus x quantity cubed. This is equal to d by dx of, now I'm going to input the series representation for this guy, which we got from the previous example. Infinite sum of n multiplied by x to the n minus 1. Okay. So this is by previous example. And now the next equal sign, I will apply the theorem. So, which is to say that I can bring this differential operator inside of the infinite sum. So, n equals 0 to infinity. By the theorem, I can move that inside the sum. So this is d by dx of nx to the n minus 1, okay? So here is where the theorem is actually being applied by the theorem. Excellent. And this is now a simple affair. We can just, again, use the power rule on x to the n minus 1, okay? So this just comes out to n minus 1 multiplied by n, multiplied by x to the n minus 2 power. Okay, so I hope that's okay. I just used the power rule of differentiation right here. Good. And this again will converge for, which converges. It's going to have the same radius of convergence as the thing we took the derivative of, which was when absolute value of x is less than 1. And that's also by the theorem. Also by the theorem. Okay. All right, so we'll do one more that deals with integration. And then I'll introduce an extra credit question, which I'll post on the webpage later. And then that will be the end of tonight's class. All right, so let's do an example where we use the integration part of that theorem, okay? Before we just took derivatives, now let's look at integration, okay? So this theorem will actually allow us to find the power series for, so find the power series for, okay, so this theorem is really nice. It will allow us to find the power series for natural log of 1 plus x. Okay, so that's really nice. Okay, so before, the first step was we wanted to realize our function as the derivative of something. Now we want to realize our function as the integral of something. Okay, so that is not that bad. So we want to note that our original function, ln of 1 plus x, okay, so does someone want to maybe tell me what this is equal to the integral of?
1 over 1 plus x.
Exactly. Very good. So
Yes.
I'm going to rewrite our function as an integral of something. Beautiful. So this is actually the same as the integral of 1 over 1 plus x dx. Great. And what's really nice about this is that we have a power series expansion for this integrand. Okay. So let me just write that. Okay, by a previous example. So this was earlier in the evening. We have a power series representation for 1 over 1 plus x. So you can just look earlier in the notes. This is just the infinite series n equals 0 to infinity of minus x to the nth power. Okay? So that's from earlier. All right, so thus we can integrate this series. You can integrate this series term by term. This series term by term to get a power series for natural log of, whoops, natural log of 1 plus x. All right. So that's the strategy. We're just going to integrate this guy term by term. Okay. And that's a simple affair. Thus, here we go, natural log of 1 plus x. This will be the infinite sum from n equals 0 to infinity. It's going to be the integral of negative x to the nth power dx. Okay, so I'm just integrating this series term by term. All right, and this is by the theorem. All right, this is by the theorem. All right, so I have moved the integral operator from outside the infinite sum into the infinite sum, and that's what the theorem tells us we can do. All right, good. Now we can just hit this with the power rule of integration, or also known as the reverse power rule. Okay, so infinite sum, n equals 0 to infinity. Well, you want to factor out a negative 1 to the nth power first, then use the reverse power rule, okay, over n plus 1. Okay, and there will be a plus c outside of the summation. Okay, plus c. All right, so is everyone okay going from here to here? I just used the reverse power rule, or the power rule of integration. Add 1 to the power, divide by the new power. Good. So we can actually do better. We can find c. All right, so to find c, you can plug in any x value. And in this case, it's convenient to plug in x equals 0. To find c, plug in x equals 0, which gives which gives natural log of 1 plus 0 is equal to natural log of 1, which is 0. Okay, thus C is equal to 0. All right. All right, so let me just write out exactly what we have found here. Natural log of 1 plus x is equal to the infinite sum n equals 0 to infinity of negative 1 to the nth power multiplied by x to the n plus 1 over n plus 1. And this is only valid, so this is valid for absolute value of x less than 1. And why is that? Because the series that we integrated, this guy all the way above, also had, also was valid only for absolute value of x, also valid for absolute value of x less than 1. And the theorem tells us that they have the same radii of convergence. Okay, so that's by the theorem. Okay, good, good, good. Awesome. So the next example is going to be one of the extra credit questions for next week, for week 6 or week 7, I'm not sure. So I'll start it off for you guys, and then you can finish it for extra credit if you want. All right, so yeah, so this will be extra credit, okay? But it's a nice example. Find the power series for arctangent of x. Okay. Okay, so let me start this off for you guys. We know that, so we want to realize arctangent as the integral of some function, okay? So we know that arctan is actually the integral of, well, I think you guys know this, 1 over 1 plus x squared. Okay? So, integrate the series for 1 over 1 plus x squared, term by term. All right? So that's pretty much what you need to do. So I leave it to you to find the series for 1 over 1 plus x squared. Okay? I actually think that was a previous example. Okay? So that's the extra credit. Yeah. So homework is due tonight, and that's all I have for tonight. So stick around if you want to ask me questions, but I will see you guys on Monday.
Thank you. Have a good night.
Thank you.
Thank
Good night.
you.
Thank you.
See you Monday.
See you guys. Thank you.